All right, so tonight we're going to look at the dot product and the cross product of vectors. So we looked at how to add and subtract vectors. We looked at how to multiply vectors by a scalar. So now we're going to look at how we're going to actually be able to multiply two vectors so we can get actually a useful piece of information. So the dot product and the cross product that we're going to look at tonight both deal with multiplication, but they come up with very different pieces of information. And the symbols for them both look like multiplication. So you'll see right here we have the A dot B. So that right there, that's the dot product. When we look at the cross product, it's going to be A with like a cross, an X in between it, which is also a symbol of multiplication. So you got to be careful with that. So when we're talking about the dot product, there's a dot between it. When we're talking about a cross product, there'll be a cross between it. So those are the two things that we're going to look at here. So the the dot product is A dot B, and it's A1 times B1 plus A2 times B2 plus A3 times B3. So basically you're multiplying the first terms, the second terms, and the third terms, and then you're adding those values together. That's what the dot product does. So the dot product is going to give me a single number answer for it, where the cross product we're actually going to get a vector out of it. All right, let's look at some examples of a cross product, or I mean, a dot product. So we've got 2, 4 is my first vector, and 3, -1, and we're doing the dot product of those. So we do 2 times 3 plus 4 times -1, and we get 2 out as the answer. Same thing if we were doing it with a 3-dimension vector, so -1, 7, 4, and 6, 2, -1/2. You just do all 3 pieces. So -1 times 6, 7 times 2, and 4 times -1/2. Add those together and you get 6. We also can look at it when it's in terms of the IJK format. So remember, if the letter's there, there's a 1. If there's no letter there, then it would be a 0. So in this case, we've got 1 I here, and we've got 0 I in this one. So it's 1 times 0, 2 times 2, and -3 times -1. So when we add it together, we get 7 out of it. Any questions on how to calculate the dot product? We're going to figure out how it's used in a little bit, but any questions on how to actually calculate it?
No, it seems pretty simple.
Okay. All right, so there are some basic properties of the dot products, just so you can see how, especially when we're dealing with multiple vectors. So if you have 2 of them, the dot product of A and A is just the length. So remember, those are not absolute value. When we're talking about vectors, that those lines mean the length. So if we do A times the dot product of A and A, you get the length of A squared. The dot product of A and B is the same as the dot product of B and A. It doesn't matter the direction you go. If you're doing the dot product of A with a sum, you can distribute just like you could technically with multiplication. So you have the dot product of A and B plus the dot product of A and C. If we're multiplying by a constant, you can pull the constant out in front and do the dot product of A and B. You could also do the constant on the other one and do the A times the dot product of the constant times B. It'll give you the same answer. And the dot product times the 0 vector would be 0. So most of those are straightforward and pretty simple, and they look very similar to if it was a multiplication type rule. And it's just the products spaced out. So when we're looking at the dot product, we also are looking at the angle between A and B. So that the dot product is going to help me find that angle. the dot product also is a function of that angle. So when we're looking at this, we actually can find the dot product, not necessarily by just adding them, but we can find it by multiplying the lengths times the cosine of that angle. So this is actually a breakdown. If you look at the law of cosines and go through the law of cosines, you actually can prove this. We are not going to actually prove it out tonight. But this is another way to find the dot product. If you're just looking for the dot products, I would not do it this way. It's easier to do it the other direction, because to find the lengths, you're still going to need the whole vectors, and you can easily do the dot product out. The reason we look at this one is it's more the corollary of this that's going to be useful. The corollary of this allows us to find the actual angle between the two vectors. And that's going to be the piece that's more important for this part here. But if we knew that we knew the lengths and we knew the angle, we could use that to figure out the dot products. So if we have the lengths of 4 and 6, and we have the angle between it is pi over 3, we can do 4 times 6 times 1/2, which is 12. So the dot product of A and B would be 12, given that information. But let's look at the corollary, because the corollary is the more important part. So if you look back at the rule, if we just divide this by the two lengths, the length of A and B, we get the corollary. And the corollary says the cosine of theta equals the dot product of A and B divided by the multiplication of the lengths of A and B. This will allow us to find the angle between any two vectors. So if we have vector A and vector B, and we want to find the angle between them, the first thing I need to find is the length of A and the length of B. So remember, the length is just, we take each of the parts and square it, and then add them and then do the square root of it. So 2 squared plus 2 squared plus -1 squared is 9. Square root of 9 is 3. 5 squared times -3 squared times 2 squared. We sum those together and we get the square root of 38. So we now have our two lengths. And we find the dot product of A and B. The dot product of A and B is 2. So now if we look at that rule, we have the dot product. We have the length of A and the length of B. So we plug that all in. And then we would do the arc cosine of that to find the value. So the arc cosine of 2 over 3 square root of 38. In radians, it's 1.46, or approximately 84 degrees is the angle between those two vectors.
Do you always give the answer in radians, or?
It really honestly depends on the application you're using it for. And purely theoretical, like we're doing here, it doesn't matter. You can do it in either one, whatever your calculator is in.
Okay.
But if you're actually using it in, this is used a lot in physics, and the actual degrees might be more useful for that than in radians.
Okay.
So, and that's just a quick switch of the calculator, just turning it from radians to degrees, depending on which value that the teacher wants. I don't believe in the, I believe in the test that actually tells you the value that it, like which it wants. So if it wants it in radians or degrees. All right, so that's how we'd figure out the angle. Now, one of the reasons why we want to find out the angles is if I can determine if two, so I can use this to determine if two vectors are perpendicular or orthogonal to it. So if they're perpendicular, that means my theta is pi over 2 or 90 degrees. Another word for that is orthogonal. It's the same concept. Orthogonal just means it's actually in the 3 dimensions. So an angle between them is theta equals pi over 2. So if we look at this rule right here, my dot product of A and B is the length of A and B times cosine of pi over 2. Cosine of pi over 2 is 0. So in essence, if we find the dot product of two vectors and it comes out to be 0, those vectors are perpendicular or orthogonal. So they're only orthogonal if the dot product of A and B equals 0. So that's another, again, it's a lot of using the dot product is to be able to look at those angles and the relationship between the two vectors. So this is another way we use it, so we can figure out if it's orthogonal or not. So if we look at these two vectors, we want to show that they're perpendicular to each other. So all we're going to do is find the dot product. As long as the dot product comes out to be 0, then they are orthogonal. So 2 times 5, 2 times 4, -4, -1 times 2, 10, -8, and -2, which comes out to be 0. So these two vectors are perpendicular or orthogonal based on that rule that the dot product equals 0 if and only if they're orthogonal. Does that part make sense?
Why does it say perpendicular by 7?
7 is the theorem.
Oh, I see.
Yeah.
Yeah.
Yeah, a lot of times they'll reference back the theorems that they were talking about. So this one, it's theorem, this 7 that they used. Any other questions with those? All right. So the other thing we can you'll notice is if the A and B go in the exact same direction, that would mean cosine the theta or my angle is 0 and cosine of theta is 1. So that means that my dot product is actually equal to the lengths times each other. And if they're going in opposite directions, it's going to be the dot product will be equal to the negative of the product of the lengths. So those are just two extreme cases where you're going in the same direction or opposite directions. All right. Another really valuable piece of information is seeing the angles that the vector has with each of the planes, the x-axis, the y-axis, and the z-axis. So if we know the angles between those axes and the vector, that's useful. What those are known as is they're known as directional angles or direction cosines. So those angles will tell me the values between it. And we get you get as many as there are axes. So if it's in 3 dimensions, you're going to have 3 of these angles for each of your vectors. That concept makes sense? So if we were doing it on 2, I'd only have 2 directional angles because I just have it to the x and the y. All right, to calculate those directional angles, the cosine of A, so we'll use A, B, and Y. So it's basically the angle to the x-axis, the y-axis, and then the z-axis. So these are Greek letters, not actually, it's alpha, beta, and I can't remember what y is in the Greek letters. Greek letter y is gamma. There we go. It's the lowercase letter. I would have gotten it if it was the uppercase letter. So it's alpha, beta, and gamma. So don't get them confused with x, y, and z. because if you do, then you're going to get confused with that one because that's actually the y term and not the y or the z term and not the y term. So all we're going to do is you're going to divide the value that they give you in that divided by the length of the vector. So the cosine of alpha is a divided by the length of vector a. The cosine of beta is the second value, a2, divided by the length of a. And then cosine gamma is a3 divided by the length of a. And then to find the actual angle, you would just do the arc cosine of those. All right. One of the things you will notice is that if you square each of those values out, you will get 1. So that is one of the rules that you have. And we also can use it as another way to write my vector. So you can write it as the length, and then inside the vector, you can actually write the angles in there. So the length times each of those will give you back your vector value. So you could actually write it as the length or the endpoint, or you could actually write it as the directional angles for each of those. So it's 2 different ways that we can write our angles. And it's also the vector divided by the length gives you those things. We already saw that. So. Any questions on how we calculate it and use or come up with these before we actually do a problem? All right, let's go through one. So in this example, we have our vectors 1, 2, and 3. And we want to find our directional angles for that. So the length of A is square root of 14. And then we're going to divide each of the values by that. So we have 1 divided by the square root of 14, 2 divided by the square root of 14, and 3 divided by the square root of 14. And then if we do our cosine of each of those, we get our angles. So alpha is 74, beta is 58, and gamma is 37 degrees. So those would be the 3 directional angles for our vector. All right. Let's do a couple examples. All right, so first thing I want you to find me is my dot product of these 2 vectors. So my dot product for this one is -1. So because the dot product's -1, what we know that this is not, they are not perpendicular to each other. Because it has to be 0 if they were perpendicular to each other. The next thing I want you to find is the angle between the two vectors. So remember, for that one, you're using cosine of theta equals the dot product divided by the lengths. So when we do the length of A, you get 7. And the length of B is the square root of 30. So when we do the arc cosine of -1 over 7 squared root of 30, we get an angle of 91.5 degrees, or 1.60 radians. Any questions on how we did those two? All right, last one I want us to do is let's find the directional angles for A. So the nice thing is here we already have the length of A. So the length of A is 7. So we don't have to do that part out. So we just have to do cosine of alpha is 6/7. Cosine of beta is -2/7. And cosine of gamma is 3/7. So alpha, beta, and gamma when we do the calculations out.
31, 106, and 64.
Thank you. And what was the last one?
64.
Okay. Awesome. I hadn't actually done it yet. I was just about to do it. So perfect. So yeah. Yep. So we're good. So this one works out pretty nice. Actually, I think it'd be 107 if we round it up to the whole number. And 65 if we round it up, because it was 106.6 and 64.6. I think the 31 was 0.0. Yeah, 31.0. Good. Any questions with those before we go on to the cross products? All right. Moving on to the cross products. So cross products are going to take our two vectors and we're going to multiply them in a way that's going to get us an actual another vector. One of the use cases of doing the cross products is it'll allow us to find a vector that is perpendicular to both of the two vectors that we're looking at. So we have A and B as my vector, and we can find a vector C that that is going to be perpendicular to both of those vectors, so that the dot product of A and C will be 0, and the dot product of B and C will be 0. So this would be how we'd calculate those out. They'd both be zeros. So if we look at this, the key is to find a vector that's going to do it. So we can eliminate the C3. So we eliminate that one. And we multiply. So we get basically what they're doing is they're taking it and they're trying to get rid of those. So this way we can get rid of the C term. And we're going to be able to come up with our vectors for it. So the first thing they do is to eliminate C3, we multiply by B3, the first part by B3, and the second part by A3. So that's going to give me my eliminating that last piece there, which was those pieces. So we can solve each of these. So C1 is going to equal, if it's going to come out to be 0, C1's got to equal the opposite part here. And C2's got to equal the part over here. So they got to equal the opposites of each other if it's going to come out to be 0 at the end. If we substitute those back in to find what C3 is, we can get that other part. So if you look, C1 is in essence the A2 times B3 minus A3 times B2. So it's the pieces that are not the ones. It's the two parts that are not the one. C2 is the third times the 1. and C3 is the 1 times the 2. So we get a vector, and now this is known as the cross product of A and B. We're going to look at another way to look at this in a second that might be a little more recognizable to you. So this is how we come up, this basically our cross product, if you want to write that down. And then I'll show you a different way to look at it as well. Now, this only works when we have a 3-dimensional vector. Because we're looking for a vector that is perpendicular to both A and B. And if you have, the only way that would work in 2-dimensional space would be if the two vectors are parallel to each other. So in 3-dimensional space, you have 2 vectors, you will always be able to come up with a vector that is perpendicular to both of them. All right, another way to look at it is we can look at it in terms of a determinant. So it's kind of like that matrix, where you're multiplying the cross values. So it's A times D minus B times C. So we do the 2 times the 4, get 8, and then the 1 times the -6, and we subtract those. And that's just another way to calculate it out, which makes it a little bit easier to see. So if we look at it in terms of a 3-dimensional one, it's the value up the top, so that A1 times the vector below it. So basically it's this one times the B2, B3, C2, C3 piece. So this is a determinant of order 3. You guys worked with matrices before? And determinants?
We did something similar in statics.
Okay. It's just a way to work on calculating them out. You don't necessarily have to work with it this way, as long as you can look at the other way and be able to figure it out. Either way works. So in this case, we have the 1, and it's times the other piece down here. So it's 0, 1, 4, and 2. The 2, basically you eliminate that column, and you have the other 2 pieces down. So whatever pieces you eliminate the column in the row, and what's left is what you're going to multiply it by. So the 2, you're eliminating that 0 and the 4, you're doing the 3, the 1, and then -5 and the 2. Now, why this is important, because if we look at it in terms of the I, the J, and the K as the cross product, you can see if we put the I, the J, and the K up on top, we can look at it the same way. It's the I times the A2, A3, B2, and B3, the J times the first and the last column, and the K times the first 2 columns. So it's just 2 different ways to look at the breakdown of them. And it's always the first one and the last one's positive, the middle one's negative. So it's the times the I minus times the J plus times the K, as we saw when we did up here and there. The thing about when we add in the I, the J, and the K, we're going to get our vectors because we can't combine them. Where in this example, we were combining them and getting a single number out. If that 1, -2, and -1 were I, J, and K, I would have actually had a vector out at the end. All right. Let's actually do one now. So I'm gonna do it out instead of. All right, so we want to find the cross product of this. So the first thing we're going to do is we're going to write it in terms of the matrix. So we have that. Any questions with how that became? All right, so what I'm now going to do is it is 3, 7 for -5 times I minus, and then it's 1, 2, 4, -5 times J, and then plus 1, 2, 3, 7 K. Everybody see where I came up with those? All right, so now we're going to do the multiplication. So we have 3 times -5 is -15, and it's minus 7 times 4, which is 28. And that's I minus, and 1 times -5 minus 8 J plus 7 minus 6 K. So I get -43I plus 13J plus 1K. So we can write it that way, or we can write it as -43, 13, and 1. So this vector right here is perpendicular or orthogonal to those two vectors I started with.
It's always I minus J plus K, right? That's just like how it is.
Yep.
Okay.
An easy way to remember it is if you're breaking it up like this, if the two columns are right next to each other, you add them. If you have to split the two columns, you subtract them. So since the J is in the middle, you're splitting the two columns, so you're using the I and the K, so it's subtracted. It's not the reason why it's subtracted. It's just a quick little way to remember it.
Yeah, it has something to do with like the direction of the
Yeah.
plane. Right?
Yeah. All right. So we actually could go through, and I don't think it's going to. The vector of A, the cross of A and B is orthogonal to both A and B. That's what we're actually calculating out. You can go through and prove that by just finding the dot. Actually, I'm gonna actually say this because I think it's kind of cool. So if we did the dot product of this, so and since it's already in the book. So if we look at this, we have the cross of A and B, and we're multiplying it by the, we're using A. So we're saying it's orthogonal to A. So when we cross these, you have A2 times B3 minus A3 times B2. They're the exact same thing. They're just reversed. So multiplication wise, that's going to come out to be 0. Same thing with this one. So that 0, that 0, and that 0. So in essence, those are all going to come out to be zeros. So this whole function, it's A1 times 0, A2 times 0, A3 times 0. So it comes out to be the actual 0 out at the end. So we could actually show, you can use that with any of the functions. So if you did it with C or whatever else, it would still come out to be the same. So that's why it works out to be, as long as that's the cross product, which we just calculated out, it's orthogonal to each of the values. The next thing that we can use, that's quite useful, is, again, we can figure out the angles between A and B if we have the cross products. So, but in this one, what you're looking at is you're looking for the length of the cross product and then the length of A and B. And you're using sine for this one instead of cosine. So if you have the cross product and the lengths, you can actually use that to find out the angle between the original two vectors as well. Just like we did with the cosine in the dot product. If the cross product comes out to be 0, then they're parallel to each other. And that's why there's no, you can't do this for a two-dimensional thing, because the only way you'd be able to come up with one would be if they were parallel, and the cross product comes out to be 0 if they're parallel. So this is just a geometric representation of that concept, where the angle would be 0, or the cross product would be 0. All right, let's do this one. All right, we want to find a vector that's perpendicular to the plane that passes through these 3 points. So we need to find a vector that passes through PQ, the cross product of PQ and PR. So the cross product would be, so that is perpendicular to both those vectors and PR. So the first thing I have to figure out is, what is the vector for PQ and PR? So the vector for PQ is, we take the points. So we have -2 minus 1, and that's I, plus 5 minus 4, J, plus -1 minus 6, K. So remember, to find the vectors from points, you're just subtracting the endpoint minus the original point. or the initial point. So in this we get -3 I plus j minus 7k.
Why is this one not minus J?
Because we're not doing the cross product for this one.
Okay.
We're going to do the cross product. We're just not doing it yet. We're just finding the actual vector for it. Because when they're giving you 2 points, the 2 points are anywhere. Basically, your vector is always basically shifting back to the original mark, the origin. So we're just trying to figure out the change between those 2 points. So same thing with P and R. So I do 1 minus 1. And that's I plus -1 minus 4 J plus 1 minus 6. Okay. So I get -5J minus 5K. And there's no I in this case. So those are the two vectors, PQ and PR. Any questions on how we found the two vectors? All right, so the next thing we have to do is then find the cross product of these.
Actually, I have a
So,
question.
yeah.
So, how did you decide essentially the directions? Like, how did you, instead of like doing 1 minus 2, you did -2 or -2 minus 1?
It just depends on how you set up your letters. So we did P, Q, and PR. So P is the initial point, and Q is the P is the initial point, and Q is the terminal point. So if I had done QP and QR, the Q would have been the first one. It wouldn't have mattered.
Okay.
And you just have to make sure your starting point, when you're doing the two vectors, your starting point has to be the same for both vectors.
Okay.
That's why. Yeah. All right, so now we're going to find our cross product. Of these. So I have I, J, and K, and I fill in the values. So -3, 1, and -7, and 0, -5, and -5. So that equals, so my I is going to be 1 times -5. So 1 times -5 is -5. -5 times -7 is minus negative or positive 35. So minus 35. And that's I. Minus, and then so I get -3 times -5, which is 15. And then -7 times 0, which is 0. J. Plus. Then I have -3 times -5, which is 15. And 1 times 0, which is 0. K. So my cross product is -40I minus 15J plus 15K. So that would be the cross product. And that would be a vector that is perpendicular to the plane, that plane. Now, any non-scalar multiples of this vector is also perpendicular. So like 40, 15, and 15, I could actually divide all those by 5. So I could have -8, -3, and 3. That would also be perpendicular to the plane. So, or I could multiply them by 10 and have -400, -150, and or in positive 15 or 150. That would also be perpendicular to the plane. So remember, multiplying it by a scalar just makes the vector longer or shorter. It doesn't change that it's actually its orientation. So it still would be perpendicular to those two vectors. That makes sense? All right. So we can look at the cross product. Remember, there's the standard vectors, the I, the j, and the k. So if we look at the cross products of those, the cross product of I and j is k, j and k is I, k and I is j. It's j and I. If you reversed it, it's going to be just the negative values of them. So you can work those cross values out. Now, it's very important though. Notice that the cross product of I and j does not equal the cross product of j and I. So unlike when we were looking at the dot product where you can reverse things and they come out to be the same value, the cross product is not the same. So if you reverse them, you do get different values out. And you actually get the negative value out. So the cross product is not commutative. So I can't do the cross product of I times that does not come out to be the original value. So if you switched it around, it does not work. And the associative law also does not work. So if you just cross product of one and then times the other, you switch the parentheses, that is not working as well. However, there are some that work, and these are the ones that work. So the cross product of A and B is equal to the cross product of negative B and A. So you're going to, if you switch them, the sign of the first one changes. You can do a scalar multiple of them. So the scalar multiple of A times cross product of B is the same thing as you can move that around. You can do the cross product of a addition and distribute the cross product through. That does work. And it doesn't matter if it's in the front or the back, the same concept does work. You can do the dot product, so the dot product of A and the cross product of B and C, or the cross product of A and B times the dot product of C, that works. So you can move the parentheses and the operation, so either the dot product or the cross product. And if you want to do the cross product of two different things, it ends up coming out to be the dot product of A and C times B minus the dot product of A and B times C. So it is not necessarily just a simple associative rule like we do with multiplication. So do keep those in mind when you're working through them. All right. Any questions with the cross products before we go on and do something known as the triple products, which is the last thing we're going to look at tonight? All right. Triple products. The product of the dot product of A and the cross product of B times C is known as a scalar triple product. So we can write it like this with the A1, the A2, and A3. So notice how this is not going to give us a vector. So the dot products give us an exact value. So this is basically taking this B and C is going to give me a vector, and then I'm doing the dot product of that and A. So we're going to get a single value out of this one. And that's evidenced by these. So this is no longer I, J, and K up here. Those are actual numerical values up at the top. What this allows us actually to do is to look at the volume of a parallel piped, which is a three-dimensional parallelogram. So we can create that from those three vectors. So we have vector A, vector B, and vector C. So notice how the base here, that's going to be the length of the cross product of B and C. Will give me the area, the base of that parallel piped. And then if we figure out the height of it, the height is the length of A times the cosine of theta. So that's going to figure out the height of this shape. So if you remember back to your geometry classes, these are called oblique rectangular prisms. I was trying to think of the name off the top of my head. So this is just another way to figure it out, knowing the vectors of each of the sides. So the B times C, or the cross product of B and C, the length of that. And then if we remember, right, the length of A times the cosine of theta is the dot product of those things. So that is where the dot product comes in. So we can figure out the volume of this based on the length of the dot product of A and times B, the cross product of B and C. All right. It's basically how you did in geometry class, except for they don't give you the height and the all the sides are vectors instead of just saying, hey, this is the length of A, B, and C, and coming up with the answers. We like to make things more complicated in calculus. All right, any questions on the formula for it? All right. Okay. Find me the area or the volume, sorry, the volume of the parallel pipe or parallelly piped of those three vectors. So remember the formula is V equals A times the cross product of B and C. So the dot product of A and the cross product of B and C. So step one, find me the cross product of B and C. Or actually, we'll do it the other way. So remember, this was A1, A2, A3, B1, B2, B3, and C1, C2, C3. So remember, it's that setup. So we don't even we can just do it all at once. All right, so what do we get when we do this out? Four times zero. So we get 1 times 18 minus 4 times 36 minus 7 times negative 18. And what does that equal? Sorry. Somebody quickly do the calculation. The faster I get to calculation, the faster you can all leave.
I think it's 0.
It is 0. So what does that mean?
It's parallel.
It's not parallel. So we're because we weren't looking for a vector at this point. We were looking for the volume of that shape, right? So if the volume of the shape is 0, that means all the vectors are coplanar. They're all in the same plane. There's no height to my shape, so there's no volume. So one of the nice things about using the triple product is you could take 3 vectors and actually determine if they're coplanar if it comes out to be 0. If it doesn't come out to be 0, you know they're not coplanar. So it's one of the ways that you can actually determine if vectors are coplanar or not. All right. And that is it. You successfully finished Calc 2. The review will be next Tuesday for the chapter 10 and 12 test. And then we'll do the test on Thursday. The final exam review, we'll do the same thing on that next Tuesday after that. And the final exam will be on Thursday. Remember, you do have the ability to exchange your final exam for the lowest test grade. I will automatically do that. If your final exam is higher than on any other tests, I will replace that. So that was the other way to improve your grade. So if you did poorly on one of the tests, do well on the final, and you will replace that and improve your grade. So if for some reason you do worse on the final than your other tests, it doesn't hurt your grade. I just keep the final exam and I don't replace any of your tests. So any questions? All right.
I have no questions. Have a good night.
You too. I would suggest going through and doing the review before class on Tuesday. This way